So we'll finally get to the X-ray tube, and I want to start, kind of circulating some of this stuff around so that you can be looking at it throughout the lecture. What we're going to try to do is go up through anode today, at least get into a portion of the anode. Might not get all the way through it, but we'll get as far as we can. Before I start circulating things around, Goldie is going to run 2 labs today instead of 4, so she's going to do 11 to 12 together and then 1 to 2 together. Does that work for everybody?
Yes.
Yeah? Okay. So, you 3 o'clock folks will get out earlier today. So, that's her plan. And again, our plan is to go up as far into the anode as we can possibly go. So chapter 7's a, kind of a longer chapter, but a lot of the stuff we've talked about, we've got to, better identify some things and explain why it is that we use certain things that we use in the construction of the X-ray tube. So that's where we're going to be today. So what I'm going to pass around are some of the components of the X-ray tube. I want you to be very careful with these for different reasons. Some of them have sharp edges on them. This one not so much, but it's kind of heavy, so be ready for that. This is a target. It's the disc that spins whenever you rotor up. That's the part that you're going to be most familiar with, so I'll pass that around. This and this are 2 variations of the same thing, and they are also targets. So you don't use these. These are from old X-ray tubes that nobody uses anymore, but again, it's something that is on the registry, so you have to be aware of it. So these are stationary anodes. These are anodes that never did rotor up. You're never going to work with a machine that doesn't have a rotating anode. So the only place that you might see these again are in a dental unit, something like that, which you're not going to be working with, but still they're on the registry, so we have to talk about them. So these are stationary anodes. This would be, and you can see where it's broken off the back, this is a rotating anode. So the opposite end of the anode, the cathode end of the anode tube is, or the cathode end of the X-ray tube is what this is. So this is it, the entire cathode. Yeah, I'm glad I have an X-ray tube. So this is the cathode end of the X-ray tube. And what you'll notice on this is that if, your eyes are better than mine most likely, but what you'll notice on this is there's 2 filaments, and the only difference between the 2 filaments is that one's longer than the other, and we'll talk about the significance of that here in a bit. But also what you'll notice is that they are kind of countersunk inside of this thing, and this thing is what we're going to talk about in a bit, and it's what we'll refer to as a focusing cup. I'll again talk about the significance of that. You've seen this before. That's an induction motor. This is considered to be a part of the X-ray tube, even though it is not inside of the X-ray tube. Okay, so just file that away. You'll see questions from now till the registry that says the only part of the X-ray tube that is outside of the glass or metal envelope is the induction motor. Right, so just file that away and don't miss it on the test. This is the X-ray tube itself. So this is an intact X-ray tube. Be careful with it because it's glass, but it's also a vacuum tube. I don't know how we got this. It's been here as long as I have, or longer than I have, but if you look at it, it looks like it's never been used. So I don't know how we got it. I don't know if, it was just a bad tube to begin with, and they took it out of the machine, replaced it, and then they gave it to us. Most of what we have is because somebody gave them to us. We used to have probably, I don't know, I'd say a good 10 of the old, like Crookes tubes, things like that, in our lab over in Pirtle, and the lab shelving was not real stable. And another faculty member and I were in cleaning the lab one day, and I was outside of the office. They were all inside of the office, and all of a sudden it sounded like a war zone in the office, and the shelving had collapsed, and all of those tubes, with the exception of the one that's upstairs, it's in 215, it's upstairs, it's the only one that survived, and yet it broke. So it mainly survived. The glass is still intact. It's just one of the ends of the tube. You can see where the glass is broken away, like right here at where in this case, the anode end plugs in. So be careful with this. I'm saying that for a lot of different reasons. One is because we can't replace it and we don't have another one. Well, we do have a couple of other ones, but this is the most intact one we have where you can see the components well. So what I want you to do is I'm going to pass those around first. And you kind of take a look at it. I'm not going to pass the induction motor around because it just fits over this portion of the X-ray tube. You've already seen it anyway. But anyway, I'm going to pass those around so that you can see them, and then I'm going to pass this around so that you can see them in context of what they look like inside of the X-ray tube and kind of put it all together. And this, I think, Maggie, was it you that was asking about the transformer and why one filament was longer than, okay, good. Okay, so this is actually a filament transformer. So when you look at this, again, your eyes are better than mine. When you look at this, what you'll notice is that you've got two coils there. And the coils, the difference between them, if you look closely enough, is that one of the coils is skinny wire and one of the coils is fat wire. But the area that they occupy is almost identical. Okay, so going back to the basics of electrodynamics, when you have high current, what you need is a fat wire because you're pushing a lot of electrons, right? So where you have high current and low kilovolt or low voltage rather, you need a big wire. But once we've got a higher voltage and lower current, using Ohm's law, then we can use a skinny wire that because we're not going to be pushing as many electrons. So since this is a filament transformer, if it was a high voltage transformer as old as this one is, it would be about the size of that cart there. So what you're seeing then is, since it's a filament transformer, the fat wire is the primary side and the skinny wire is the secondary side. So they occupy about as much space. It's just that one's a big wire and one's a little wire. Okay? So I'll pass that around too. I'm going to pass it around last, because that's not really what we're talking about today. So let's go like this. What I want you to notice on the anodes is what the anodes look like. So stationary anode. Stationary anode, the problem with stationary anode is all electrons you send from cathode to anode bombard in exactly the same spot. And since they do, what you get is, I'm trying to make that where it can be seen on the video, is a melting of the anode. All right. So the reason we rotate the anode is spread that area of bombardment out so that it extends the tube life and it doesn't melt the anode. We're still going to have some problems with it. So the second anode is also a stationary anode, and you can see the impact point of, this is a little bit more advanced, but the impact point of two separate filaments for large and small focal spots. So what we use to control our sharpness or recorded detail, aside from positioning, low OID, adequate SID, is the size of the filament. So once you get the cathode into the X-ray tube, that's what you're looking at, is filament size, large and small focal spot. Okay, small focal spot for sharpness or recorded detail, large focal spot for large exposures. So there's that one. Again, I think I took all the glass out of, well, the glass that you can get to out of the cathode into the X-ray tube. So once those kind of circulate, then I'll pass around the X-ray tube, and then I'll pass around the filament transformer just so you can see it. So what we're talking about then is the X-ray tube. We're going to talk about external components. We're going to talk about internal components and why we have them the way we have them, the material that we use, why we use those materials. Some of the things we're going to talk about are not in the book, but if you know anything about metals, especially tungsten, this is going to make a little bit of sense to you. So external components, what we have then in the external components of the imaging system itself is we have to have something so we can move it around, right? So that's your support system. So we have a number of different types of support systems. If you happen to go to your doctor's office and they have a low ceiling, they can't use the type of support systems that you're most used to seeing in the hospital. You have to have a relatively high ceiling. In addition, like our lab upstairs, when we built this building, you know, what you see, you know, of course, is the ceiling's probably 12 feet tall, right? But what you don't see is above the ceiling tiles, it goes up probably another 12 feet, and there's $250,000 worth of construction holding, you know, that support system up. Okay, so you have to have a superstructure above to hold everything up. So there's a lot of metal up inside above the support system. So if you go to your doctor's office, and doctor's office 1 story tall, unless it's, you know, 30 feet worth of 1 story, you're just not going to have that type of x-ray tube. So I know I'm taking these out of order according to the textbook, but one type of system that you just don't see a whole lot of, and you don't see a whole lot of those even in a doctor's office, is what we refer to as just a floor-mounted system. So a floor-mounted system, what you've got is a track, and you got this tower coming off of it, and then the x-ray, and we'll call this portion a crane, but the x-ray tube hangs off of the end of it. So you've got a little bit of motion this way, you got a little bit of motion this way, and you've got some sway so that you can position, but it's very limited. So, you know, if you were to have that as your primary x-ray unit inside of a hospital, you'd have a hard time doing like surgical lateral hips, things like that. It just wouldn't work well. Okay. The other thing, this is what we used to have over in Pirtle, and then the other thing with it is that our system over there would jump the track sometimes. So, you know, students moving the x-ray tube, and all of a sudden you hear a crash and it jumped the track and it fell over. So we had to pick it back up, put it on track. So that's a little unstable, right? So what is in the textbook is ceiling to floor mounted system, so that instead of just having it on a track, it's got a track up top and a track on bottom. Otherwise it's identical, really. It's got the crane system, but it's got a support at the top and a support at the bottom so it won't fall over. But it's still very limited. Both of those you're only going to see in a doctor's office, somewhere that they don't have the deep pockets in a big building like what you're going to see in a hospital. Okay, so you don't see a whole lot of those. You're not going to see them probably while you're in school, unless we add another clinic. Just know that we've got floor-mounted systems, ceiling to floor-mounted systems. What you're most familiar with is the overhead crane system. So overhead crane system has 2 sets of 2 rails. All right, so go into the lab, take a look at the ceiling, and what you've got then is a set of rails that goes across the room, almost from the windows to the door, right? And it's got another set of rails that goes, I'd say, about 2/3 of the way to the sink and almost to the wall on the other side. So 2 sets of rails, total of 4 rails. So these are stuck to the ceiling, and then these roll on those. Okay, so if your crane system is here, and this is as if you're laying on the floor looking up at it, if your crane system is here, then you can take your x-ray tube and you can move it this way, and then you can move this set of rails up and down that way. Very flexible, ceiling mounted systems, most common, most of what you're going to see in a hospital, anywhere that they have, you know, the room, the ceiling height, and enough money to put one of those in. So that's what you're most familiar with. But there's also C-arm systems. C-arm systems can be portable, like what you're seeing on page 113. Probably at this point, what most of y'all are most familiar with is the portable, you know, portable fluoroscopy C-arm system. There are C-arm systems that are not portable fluoroscopy. Some, if you venture back to special procedures, interventional, cardiac catheterization, you'll see ceiling mounted C-arm systems. Okay, so they're not all portable. But the thing with the C-arm system is that what you've got in most cases is a set source to image receptor distance, right? So you can't expand it out or bring it in. There are kind of variations of diagnostic systems, is what they refer to as Tramex system. It's kind of a C-arm system, but it's kind of a digital C, right? So instead of being a C like that, it's kind of squared off. And what those do is they're not fluoroscopy, they're radiography units. And what they have on one side is an image receptor and on the opposite side an X-ray tube. So they call them Tramex because they developed them thinking that they would be good in trauma situations where you didn't have dedicated X-ray units, right? So it carried its own image receptor, it carried its own phototimers, everything, so that you could do cross tables and things like that. It moved kind of like a C-arm, so you could go AP to lateral pretty easily. Flexible, it just never really caught on. I think Mother Frances Christus had one for a while, but once they replaced it, I don't think they went back with it. Anybody at Christus, Maine? Do y'all have that anymore? No. So it just didn't catch on all that well. So those are your types. So you have floor-mounted ceiling, two floor-mounted ceiling systems, and then C-arm systems. All right. So regardless of what they, what type of support system you have, all of those are going to have what we refer to as protective housing. All right, so you don't ever see just the X-ray tube all by itself, right? So again, be careful with this. I'm gonna let it go around. If you happen to drop it, we're not going to take you outside and throw you off the roof or anything, but it's going to sound like a bomb went off. Okay, so don't drop this. It's a vacuum tube, so it's like dropping a light bulb, only it's with very, very thick glass, and it's going to make a lot of noise. Thank you. All right, so the things I want you to pay attention to in the X-ray tube, obviously the components I was talking about, but also turn it and see how well balanced the rotor end of the X-ray tube is. It's kind of like, you ever get a bug in your cup and you want to pour him out, and you turn the cup and the bug doesn't move, right? You're trying to get the bug in a specific place so that you can pour him out, and the bug doesn't move. It kind of does the same thing. You turn it, and it's so well balanced that the anode doesn't move well, right? And there's a reason for that, and we'll talk about that as we get to it. All right, so protective housing is what you normally look at and you think X-ray tube. So the protective housing is that thing that's directly above the collimator housing. And it is where the X-ray tube is housed. Okay, so you got the X-ray tube inside the protective housing. The protective housing does a lot of stuff. It protects the X-ray tube against you, and it also protects you against the X-ray tube. So, let's say you get in a rush, you're in a trauma situation. Sometimes trauma situation, you get ahead of yourself, right? So you push the button, you're dragging the tube across the room, your finger pops off the button, and the X-ray tube comes to an abrupt stop. That's rough handling, right? And the housing supports the X-ray tube in a way that if that happens, it's not just going to snap the X-ray tube off. That's not to say that you want to get in practice of doing that, but if it happens once in a while, it's not going to damage the X-ray tube. Okay, so it protects the X-ray tube against rough handling. It's in there and supported in such a way that it protects against that. But it also protects you from the X-ray tube. So when we send the electrons across the tube, we go across the tube, at the point of impact, where the electrons, I think it said X-rays across the tube. It's not X-rays, it's electrons. When we send the electrons across the tube, at the point of impact, an X-ray photon has equal likelihood of being created and not really emitted, but projected in any particular direction, right? So if we have, let's say we send one electron across the X-ray tube, it could go anywhere, the electron could, or the X-ray photon could. Okay, so now apply that to the billions of electrons we're going to send across the tube. All of those electrons have equal likelihood of going in any particular direction. But we only want the ones that will go through what we refer to as the window of the protective housing. That would be this area right there. There's obviously not a hole there, but what there is maybe some glass there in the protective housing that will allow the photons, X-ray photons, to pass through that. So we want to block all of those except for the ones that would come through that window, okay? This is what we refer to as isotropic emissions. So isotropic emissions just means equal intensity in all directions. So you got a puddle of water and you got a big rock. You drop the rock in the water, where does the water go? Everywhere. That's isotropic emissions, okay? Now, really they come off of the anode in that way, but they're not going to be projected out of the, past the anode in the same way. Okay, so what did you notice about the anode when I passed it around? The big disc.
It's heavy.
It's heavy. Why is it heavy? It's made of metal, right? So what shows up real well on X-rays? Better than anything else? Metal, right. So the likelihood of these X-rays going through the anode, very, very good? No. So the anode itself not only creates the X-rays, but it eliminates some of those isotropic emissions. So if we've got our anode here, then it's going to block some of those X-rays from going back that way. They're still, though, going to go off in every other direction. And potentially, if you're in the room, if you look back to chapter 1, the kid getting his arm X-rayed, and the other picture of Edison in the fluoroscopy where the X-ray tube is inside what looks like a wooden box. Where are those X-rays going? Everywhere. Everybody in the room is getting blasted, right? So we don't want that. We want to limit the X-rays just to what's coming through the window and eventually hitting the patient. So one of the jobs of the protective housing is to limit radiation that is going anywhere except for through the window. And if it gets out from anywhere except for the window, we're going to call that leakage radiation. And it has to be no more than 1 MR at 1 meter, which is the same as 1 R at 1 meter, which is 1 milligray in air at 1 meter. Okay, so it limits leakage radiation. It stops the isotropic emissions up to this point. If we've got isotropic emissions coming out from anywhere on the protective housing greater than that, then we've got a problem. Can't read my writing, or is it too small? It's 1 R at 1 meter, or 1 milligray in air at 1 meter. So they're both the same thing. Facial expressions are always fun. All right, so it limits isotropic emissions, and we want to limit it just to the window, but we do allow for a little bit of leakage. I've not tried this with digital image receptors, but with screens and films way back in the day, I tried to detect how much leak, not really how much, but presence of leakage radiation. I got nothing. With the sensitivity of our digital image receptors, I would suspect that you could probably pick up some leakage radiation if you were to point, let's say, the X-ray tube at the wall, a wall that's very far away, right? So maybe get 10 feet and, you know, point the X-ray tube at the wall, or even at the ceiling with a image receptor directly below the X-ray tube. You might be able to detect some leakage radiation. So that's what it protects from. It protects you from the tube, and it protects the tube again from you. All right, so another thing that doesn't come until later in the chapter, and we talked about it earlier in the semester, is that the main thing that kills an X-ray tube is heat, right? So it also protects the X-ray tube from heat. So the construction of the anode is going to do a part of that. You know, we rotate the anode so that we spread out the heat, and then we radiate that to the glass or the metal envelope. Then we conduct that into the oil, and that's where we are right now. So what we have inside the protective housing is the oil, right? And so we conduct the heat into the oil, and then we have that fan, and it may not be an active fan, it may be a bellows that blows across the oil to cool it down. It cools the oil cools the X-ray tube down, so we're using all three. We've got conduction, we've got thermal radiation from the anode to the glass, conduction into the oil, and then we've got convection as we blow the air across, right? So it protects from heat, protects from rough handling, also protects from electric shock. So it protects from a lot of different things. All right, sometimes though, in addition to the leakage radiation, sometimes, you know, I've only seen this once or twice, but sometimes we may have a mechanical breakdown of the protective housing. What I mean by that is, you know, it's not really mechanical, it's pretty static, but we may have a loss of integrity of the protective housing itself. What I mean by that is we're leaking oil. Okay, so you walk into an X-ray room, an X-ray tube is parked over the table. You see a puddle of oil on oil, for the non-locals. You see a puddle of oil on the table, that means this thing is leaking, most likely. Either that or somebody spilled some, right? So if it's directly under the X-ray tube, you shut that room down immediately. You don't bring a patient into the room. Why? What's the purpose for the oil?
Heat, to reduce heat.
Right, it actually absorbs the heat, right? Which means that you start making X-rays with this stuff dripping on the patient. And what's the patient gonna get? A burn. And what are you gonna get?
Fired.
Fired in a lawsuit, right? So, yeah, so, you know, that's immediate shut down the room. If you walk into the room, you see oil under the X-ray tube, that room is dead for the day, all right? So that's protective housing. It provides mechanical support, protects against rough handling, protects against excessive heat, protects against electric shock, all that stuff, okay? So inside the X-ray tube, or inside the protective housing, we obviously have the X-ray tube. So the X-ray tube, they can be made of a couple of different things. What I passed around, or is still going around, is a glass envelope. The envelope is just the tube itself, right? That's the part you can feel, okay? So just file that away. It doesn't look like an envelope, you know? It's just file it away. They call it envelope. So it can be either glass or metal. Glass is pretty traditional. You know, a few years back, they started going towards a metal envelope. We'll talk about why here in a bit. But the glass envelope, the purpose for the envelope is to keep this oil out, but also to maintain a vacuum. Okay, so it's a vacuum tube, just like a light bulb. It's a vacuum tube. With a vacuum tube, instead of a pressurized tube like what they used back in the early 20th century, what we get is more consistent exposure. they used to use partially pressurized tubes, so they had gas inside of it. And what happened with those partially pressurized tubes is that we got erratic flow of electrons from cathode to anode, okay? So it wasn't consistent. The gas that was inside the tube interfered with the flow of electrons from cathode to anode. And if it interferes with the flow of electrons, then it will also interfere with the creation of X-rays. So we get erratic exposures. You set 20 mass and you might not get 20 mass. So they didn't want that. So they went to a vacuum tube. So the envelope maintains that vacuum. Now sometimes the X-ray tube will start to leak. And by leak, it's going to lose some vacuum and it's going to suck some oil inside. As it does that, what we get is a gassy X-ray tube. So if we have if we have a gassy X-ray tube, we're back to a partially pressurized tube. And what do we get? Erratic exposures. Okay, so you walk into X-ray room one day, you make an exposure, and you get a perfect exposure. You know, you set a foot technique and you get exactly the index number that you should have gotten, and then you go back in tomorrow and you, let's say we're doing a follow-up on the same patient, you use exactly the same technique and your index number is half of what it was before. There's only one of two reasons it would come out exactly half, and one would be erratic exposure because of a gassy X-ray tube, and the other is because your rectifiers fail. Okay, so that's something that we talked about after. I talked to somebody about after class, I think after the test. Generally, if your rectifiers fail, then you can diagnose that as, you know, all of your exposures now come out exactly, your index number would indicate that your exposures are exactly half of what they should have been. So you're going from direct current to alternating current across your X-ray tube. Okay, so again, file that away. Consistently half, if all your exposures drop to half of what they should have been, your rectifiers aren't working. So you pull on rectifiers. Okay, so now that that's gone most of the way around, I'm going to go ahead and start this. This is kind of heavy too, but this is not going to explode if you hit the ground with it. But again, take a look at the difference in the filaments. Yeah, watch your toes. Look at the difference in filaments, and it, you know, hopefully will make a little bit more sense. Okay, so metal tubes. We'll talk about why we make the change to metal tubes here in a bit, but just know for right now, hopefully we'll get to this today, that we've kind of made a change in a lot of the X-ray tubes. The envelope is now metal instead of glass, and there's legitimate and good reasons for it to be that. So we'll talk about the internal components of the X-ray tube, and that's what's been coming around. The tube itself, we've got the cathode, and that's the negative side of the X-ray tube. That is your source of thermionic emissions. That's where our electrons come from. It's this thing right here. But again, you notice that it was kind of countersunk inside of something else. So we're just going to erase that and just go with that filament. So it's countersunk inside of something else, right? So that something else is what we refer to as a focusing cup. All right, so the filament is embedded in a focusing cup, and what we have inside of that focusing cup is generally two filaments. One large filament, one small filament. Large filament for high exposures, and small filament for sharpness of recorded detail. And we'll talk about those here in a bit. So we've got the filament, we've got the focusing cup. The purpose for the focusing cup is to keep the stream of electrons compressed so that they travel across the X-ray tube and impact the part of the target that we want them to impact. Okay, so what are electrons? All negatively charged. So what do you know about electrodynamics or electrostatics? Like charges do what?
Repel.
Repel. Right. So if we've got all, let's take the focusing cup off, and if we've got all negative charges, what are they trying to do? They're trying to repel from each other, right? They're trying to push each other as far apart as possible. The more we push onto it, the harder they're trying to push from each other. All right, so let's say we make an exposure and we don't have a focusing cup, and we send all those electrons across the tube and we don't have anything pushing them together. What's going to happen as soon as they leave that filament? Yeah, right. So it's almost, not exactly, but it's almost like we have isotropic emissions here, right? They're going to travel, they're not going to travel backwards, so it's not really isotropic emissions, but they're going to spread out really, really rapidly. So think about the difference between a regular light bulb and these light bulbs. Okay. 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 So how's my shadow look?
Small.
Okay, it's small, but is it sharp?
Yes.
Yeah. Okay. It's coming from just one little spot, right? Now, what I want you to do is hold your hand over your desk. What does your shadow look like?
Hardly like a hand.
Hardly like a hand, right? Why? Because the light's coming from everywhere, right?
As opposed to that.
So the smaller the light bulb, the smaller the filament, the smaller the area of impact, and the smaller the spot that we create X-rays, the sharper the image is going to be, okay? So again, if we send the electrons across the tube, some of those are going to go down to the glass, and that's going to be disastrous for the X-ray tube, as we're going to talk about in a bit. But some of them are going to go up there. And then we get isotropic emissions, and what we have is basically a fluorescent X-ray tube. Those lights, right? But if we can confine them to just a small area of impact on the anode, then we can improve our sharpness of recorded detail. Okay? So the focusing cup, the purpose for the focusing cup, you saw again that it extended out past the filament. The purpose for the focusing cup is to kind of compress those things down so that whenever they travel across the tube, once they get past the focusing cup, are they going to spread out? Absolutely they will. But if we can keep them compressed as long as we can, then they have less time to spread out, and therefore we increase our sharpness of recorded detail. Okay? Focusing cup. Compresses a stream of electrons, so our electron cloud, our thermionic emissions, don't get too big and broad so that we lose sharpness of recorded detail. Now, this may be getting a little bit ahead, but let's say we're making an exposure with very high MA. What does MA control? Quantity. It's the quantity of electrons we're going to put on that filament. Okay? So the focusing cup's going to be low voltage, maybe 25 volts, something like that. It's going to be very low voltage, but you know the voltage through the filament's very low too. Right? So it doesn't overcome it, right? This doesn't overcome that. But what if we put so many electrons around this? Where'd my green marker go? Keep color coding, right? What if we use very high MA and we put a tremendous number of electrons on this so that our electron cloud is massive? And then I send them across tube. Some of them are out past the focusing cup. What's going to happen to my sharpness of recorded detail? Yeah, it's going to decrease. It's what we refer to as blooming of the space charge. Just like a flower, it's blooming of the space charge. It gets too big. There's two things that are going to cause that. One is very high MA, and the other is sitting on a rotor button too long. Okay,
It's like
so
building up too much.
what's
Like
that?
Building up too much.
Building up too much, exactly. So, you know, you walk into the room and somebody else is positioning, and you're watching the patient, and you start rotoring up. You're doing a chest X-ray, you start rotoring up before you tell them to take in a big deep breath. So what's your second instruction to the patient after a big deep breath?
Breathe.
Blow it all the way out, taking another deep breath, you're still rotoring up. You're creating a ton of heat. With a ton of heat, you're creating a big space charge, right? I'm getting some looks like, I did that. You're creating a big space charge, and what you're creating is blooming, and you're losing sharpness of recorded detail. Okay, so for a lot of different reasons, your rotor time should be as short as possible. That's one of them, is because long rotor times are going to give you blooming. It's going to create a lot of heat too. You're going to lose sharpness of recorded detail. You're driving heat. What's the main thing that kills X-ray tube? Heat. Short exposure times. Is there a time to stand on a rotor button for a long time? Relatively long time?
You're trying to do a child and trying to
Bingo.
get that.
Bingo. Yeah. With kids, yeah. Because how do kids, you got a screaming child. When do you want to make the exposure? In a split second that they go, eh, right? So kids, they exhale forever. They go, eh. They run out of air. Right? Well, if you wait till, you missed it, right? So you have to be on that rotor button. If you're in ICU and the patient's on a vent, right, you have to be on that rotor button. If you're in surgery and you're waiting for the doc to inject contrast into the patient, you've got to be on that rotor button. So there are times that you need a longer prep time, but most of the time you do not, right? So blooming of the space charge, high MA, long prep times, lose sharpness, recorded detail, shortens tube life. Okay, so what happens? What might you diagnose if one day you walk into a room and all of your images look fuzzy? Every single image looks fuzzy. You're not over prepping. What might have happened? I think you're saying it.
No voltage, like you didn't have
No
that.
voltage on the
No.
focusing cup failure. Okay.
So when there's no voltage, it doesn't have like the.
It's not compressing them anymore, and so we're back to almost as bad as, excuse me, not having a focusing cup at all. The electrons going everywhere. Okay. Now the filament itself. What's the filament made out of? Tungsten. Same thing as the anode. It's made out of tungsten for a number of different reasons. One is it's got a very high melting point. The melting point of tungsten is like 3,410 degrees Celsius. So you look at, I don't know, you do the math, 7,000 degrees Fahrenheit is a lot, right? So very, very high melting point. That's one thing, but it's also a good conductor. We want that. We don't want a lousy conductor because we have to have a space charge. We have to have a lot of electrons. We have to have that flow of electrons. So it's got to be a good conductor. The problem with tungsten, anybody ever done any kind of welding? Okay. Any TIG welding?
I haven't, but
No?
that doesn't make a mistake.
Yeah, MIG and stick. Okay, so if you ever do TIG welding, what you get is you get this big roll of tungsten. You're nodding like you know where I'm going with this. Yeah, it feeds, yeah. So you get this big roll of tungsten, don't knock it over, whatever you do. Because if you do, you gotta go get a broom. Tungsten is brittle. Okay, so it's got a high atomic number, but it's very brittle. Anybody got a tungsten ring? It's almost certainly not pure tungsten,
Yeah.
because if you drop it, it's going to shatter. Okay, so again, back to the rough handling of the x-ray tube. You're dragging a tube across the room and your finger slips off the button. You got this little bitty squiggly wire inside, and your x-ray tube comes to a sudden stop. There's a very real chance you're going to dislodge that from, its connector or break it somewhere. So it's not pure tungsten. It's got a little bit of thorium in it. So Bushong says that the thorium improves thermionic emissions, which it probably does. He's smarter than I am. It doesn't take a lot, but he's probably right. But the other thing it does is it gives stability to it. It's less brittle with a little bit of alloy. Right? Okay. So, where else do we use tungsten? Anode. So we're going to talk about that again in a minute, and we're going to use it in the anode for some of the same reasons and some reasons that are a little bit different as well. All right. So. Let's see, the other thing. Okay, so high melting point, but we're still going to melt the filament eventually. Light bulbs, incandescent light bulbs, the ones with a filament, also use tungsten. Okay, so do they last forever? The answer is no, they don't. They don't. So one burns out and you unscrew it and you look at it, and what do you see? You got a light bulb, it goes like that.
Coil's broken.
Coil's broken, okay, so it's got you got an open filament, and by the way, open filament is a reason for tube failure. Why is it a reason for tube failure? Because of the main cause of x-ray tube failure is heat, right? So we burn out a filament. So if we can burn out a filament here, we can burn out a filament here. That's what we refer to as open filament. Your tube doesn't shoot anymore. You can diagnose open filament this way. Is if you set a technique that would work on large and small filament, and it'll work on one but won't work on the other, you got a filament that's burnt out. So, it doesn't completely kill the tube, but it does kill one of the filaments. All right, so you got a burnout light bulb, you got the base of the light bulb down here, and what do you see? Yeah, it's tanning, all right? So that's a word that you don't normally associate with light bulbs, but what you see, especially around the base, is that dark area. And what that is part of that filament that comes out and it kind of coats the inside of that light bulb. Same thing happens in your x-ray tube. So as you heat this thing up, every time you heat it up, and especially if you heat it up a lot, that's happening. You're vaporizing the filament, and it's going to coat the inside of the x-ray tube. Okay? So inside of the x-ray tube, if it coats the inside of the x-ray tube, then that's a very thin layer of metal that you've laid down inside of it. What was it before? All glass, right? So glass, very radiolucent, very radiopaque. Radiolucent. Metal, very radiolucent, very radiopaque. Very radiopaque. Okay, so this is a very thin layer. I kind of drew it thick, but it's a very thin layer. Will the x-rays still go through it? Yes.
Yeah.
But what it's going to do is it's going to absorb some of those low energy x-ray photons before they get out of the protective housing, before they even get out of the x-ray tube. Okay, so what does that sound a little bit like? What's that? Filter. Yeah, it's filtration. It's a type of filtration. It's what we call added, increased inherent filtration. We have two different types of filtration. We have added filtration. We have inherent filtration. Inherent filtration is what we can't take away from the imaging system and still legally make an x-ray. And there's two components of that. We can't take it out, And we have to have that much in order to legally make an x-ray. And that amount is 2.5 millimeters of aluminum equivalent, okay? So with tube life, let's say a brand new x-ray tube comes up to 2.5 millimeters of aluminum, because that's what we have to have. Over tube life, because of tanning of the x-ray tube, then that 2.5 millimeters is going to slowly climb, 2.9 and so forth. It's going to increase the inherent filtration in the x-ray tube. It's going to do something else too though. And that is, it's going to change the electrical potential and the electrical tendencies of the x-ray tube. So again, back to electrodynamics. Glass a good insulator, or is it a good conductor? It's an insulator, right. Now you coat it with metal. What does it become? It becomes a conductor. It's not a semiconductor because now it's coated with metal, right?
And the metal's fully.
And the metal's fully a conductor, right? So now our electrons, okay, can I get rid of some of this stuff? Okay, where we had glass before, our electrons, which are all negative, completely ignored the glass because it was an insulator, right? And now we laid down a layer of conduction on it. What might happen to our stream of electrons, or some of the electrons, instead of going from cathode to anode, they may go from cathode to the tube. Okay? That's arcing. That's what we call arcing. Arcing is, again, where the electrons don't go from cathode to anode, but some of them go from cathode to the glass. Now we got a short circuit. So what caused the short circuit in this case?
The tanning.
The tanning, which was caused by vaporization of the, probably a little bit on the anode too, but vaporization of the filament, which was caused by heat. So again, main cause, heat, right. So arcing though is going to be your most common cause of instantaneous tube failure, tube death. You're shooting just fine, then you're pow, you got nothing. You got a short circuit, your x-ray tube is dead.
So did it
Arcing.
explode the casing?
No, it's not likely. I mean, I suppose it could, but probably not. But yeah, it's done at that point. No arcing. So, yeah. So I said that we've got two different types of tubes. We've got glass and we have metal, right? All right, so just kind of file this away as one of those things that it is because it is. If you could engineer something, engineer a component that is, it's made of a conductor, but you engineer it in such a way that these electrons that are going from cathode to anode are not attracted to that metal envelope. They ignore the metal envelope and they go from cathode to anode, even in the presence of the metal envelope. Would it matter if you put a really thin layer of metal on top of the metal? The answer is no, it would not. So the benefit of the metal envelope is it completely removes the likelihood of arcing. It's just not going to happen, right? So, if you put a thick layer, maybe, but the thin layer, even when you unscrew your light bulb, most of the time you can still see through that, even though it's dark, right? So the benefit of the metal envelope is that it doesn't have a problem with arcing, right? Arcing. Are we still going to have tanning?
Yes.
Absolutely, absolutely. But are we going to have arcing? And the answer is no. Okay. All right. So Focusing cup, da-da-da. Okay, so filaments usually side by side, you saw that. You're gonna see in the Bushong that he does mention that some filaments are stacked. All of your X-ray tube are gonna be bifocal, meaning you have two filaments, right? So you got a large filament and a small filament, and again, you saw that. But some of them will have, instead of the filaments being side by side, they'll be one on top of the other. And in those cases, what we have is a target that has two bevels on it, one very steep bevel and one less steep bevel. And in those cases, you got a filament there and you got a filament here. Unless you're working in a place that, you know, these are very specialized X-ray tubes. And unless you're working in a place where you've got very small, like fractional focal spots, you're probably not going to be working with one of these. So if you go to work in an interventional cardiac catheterization, something like that, you won't know it, but that's probably what you're going to have is a bi-bevel X-ray tube. And that's what he's talking about. So most of your tubes, the filaments are going to be side by side, just like the one I passed around earlier. Okay, but that's what he's talking about in bi-bevel X-ray tube. They're all bifocal, but they're not all bi-bevel. Okay. All right. Everybody good so far? We're right at an hour. Any questions so far? All right. Good. Then just file this away as well, because I see this in a lot of registry review books, and I know I stress that kind of sometimes. Let me finish my thought or I'll forget it. But if I see something consistently in registry review books, there's a very good chance that it's going to be on a registry. So he mentions on page 114 that that going back to our focusing cup, that in X-ray units that need very rapid exposures, you know, rapid, what we refer to as serial exposures, which is image, 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 right? It's not fluoroscopy. They're still radiographic images, but they're in quick succession. So like cardiac catheterization, you know, they want to make an image and they want to make another image, another image, another image, and they're like fractions of a second in between. So where they put the circuitry that controls the timer is right there on the focusing cup, okay? So when he says in grid controlled tubes, the focusing cup becomes the exposure switch, that's what he's referring to. Doesn't mean you reach inside the X-ray tube and, you know, hit that button. It's just, that's where that circuitry, you know, controls the starting and stopping, what we refer to as the interrogation and extinction of exposure is at the focusing cup. So you had a question?
Yes, on the, earlier you said there was an alloy with tungsten and then it was thorium or?
Thorium.
In the book it says a different metal?
Just radium.
Rhenium. Oh, yeah. Thorium. I think I've got them backwards. Thorium may be the anode. Rhenium. Rhenium.
So it's not
Yeah,
thorium?
thank you.
So what is thorium?
The anode is also going to be you know, I always want to flip those. The anode or the target area is going to be thorium. I always want to flip those two. I don't know why.
It says the filaments are made of thorium.
Yeah, thoriated tungsten. Yeah, okay. Yeah, it is thorium. It's thoriated tungsten. You're on page 114?
On 117, towards the bottom, it says radium.
Oh, but this is talking about the, is this talking about the anode?
Yeah, let's talk about the anode. on
Okay,
117.
okay.
Yeah. All right, okay, I confused that enough, I got it right, don't,
Okay, anode is.
Don't screw me up.
Filament is thorium.
yeah. Thorium, filament, rhenium on anode, in part for the same reason, gives it strength so it doesn't shatter. Okay, all right. Anybody else want to confuse me? All right, let's see. Okay, so a couple of things. And we talked about these in the last section, space charge effect and saturation current. So space charge effect, in the last section, we talked about space charge effect, making sure that we only send the number of electrons across that we want to send across, right? So it's kind of got a couple of different components to it. And that is that at high filament current, we can't send any more electrons across tube. Okay, so high filament current, you know, we get to a point where we can't repopulate the filament quickly enough. Okay, and then saturation current is that once we, and that's during prep, but once we make our exposure, once we send the electrons across the tube, then we've made room for more electrons. Does that kind of make sense? But we can have a current high enough or an exposure that's high enough that even after we apply the voltage, we can't repopulate the filament enough. You're truly at tube limit. You can't send any more electrons. Any Trekkies in here? Star Trek fans? No?
I think everybody's-
Okay, yeah.
I think
So,
everybody's too young.
I've given them all they got. Yeah, that's all you can send. You can't send any more. You can't repopulate it enough. So back to our falling load generator. You know, if you were to keep it at that 1200 MA, it just couldn't keep up, right? And that's why it drops. And it continues to drop just because you can't repopulate the filament with enough electrons to continue that
So
exposure.
what was the blooming again?
Blooming is where you have that high MA and the electrons are, your electron cloud, your thermionic emission is so big that it kind of escapes the focusing cone. So you're kind of trying to make a connection between the two, and there is a connection there. You know, in both cases you got very high MA, but in one case you're talking about the actual exposure that you can create. But with the blooming, you're talking about the resulting loss of sharpness reported detail. Okay. Okay. Got it? Ish?
Ish.
Yeah. So always associate blooming with loss of sharpness reported detail. So between the two, I'd say 95% of the questions would be pertaining to blooming and loss of sharpness reported detail. 5% or less saturation current, space charge effect. Matter of fact, after this test, I'm never going to ask you about saturation current. Okay. We're almost out of time. I thought we were going to make it to anode, but we are not. What is our actual time on there? Huh?
Lisa, what's the time?
Our time on there is 1 hour and 4 minutes. Let's just not get into it. Let's pull up there. Any questions?